All right, so the last piece of the waves and sound waves unit that we're going to talk about relates to music. So we're going to talk a little bit about musical instruments. This is something that we could probably spend weeks upon weeks discussing, but we're just going to do a quick overview of some basic ideas with musical instruments and how all this really relates to what we've been talking about and what we've been doing so far in class is that basically every musical instrument consists of one of two things. It's either a vibrating string or a vibrating column of air. Okay, drums are an exception. They're technically considered to be like a membrane, but basically every other instrument falls into one of these two categories. So strings would be things like guitars, violins, pianos, etc. Vibrating columns of air, you have things like all of your brass instruments, trumpets and trombones and flutes and clarinets and saxophones all fall into that category of a column of air. And the way that all of them work basically is they are creating standing waves within the instrument, either in the string or in the column of air. And what ends up happening is you only end up hearing the standing waves for certain resonant frequencies. All right, and all of this is really based off of the length, and we'll get into that a little bit later. But the important thing for this first piece is that you know that inside any air instrument or any instrument that consists of strings, resonant frequencies are what you ultimately end up hearing, and that results from standing waves being created within that instrument. And just as a refresher, this is what a standing wave looks like, okay? It's that basic idea that you have a steady state created within this particular string here. This would be the fourth harmonic of the standing wave, but we'll get into that a little bit later. So as I started talking about before, which resonant frequencies we hear for a particular instrument when they're playing a particular note depend on really two things. The first is the ends of the strings of the pipes, okay? And so depending on the shape of the instrument and how exactly it's created, we can either have open ends, in which case the wave is free to move on the ends, or closed or fixed ends. So like a string instrument, both ends are going to be fixed. However, when we get into the instruments that are like a flute or a clarinet, the ends could either be open or closed. So for example, a flute is open at both ends, whereas a clarinet is open at one end and closed at the other end. And that's not something that I expect you to know. That's something that you'll be given within the context of the problem. You certainly don't have to have a comprehensive knowledge of different musical instruments, but that is one thing that affects what notes we actually hear. The other thing is the length of the string or the pipe. And I think the best example of this is if you look at like a massive organ that maybe they have in an old church. You see all the different pipes laid out for you, and they're all different lengths. And the way that you play different notes is you blow air through pipes of different lengths. That's how you do it on an organ. On a piano, if you were to open it up, you'd see a bunch of different strings that were all different lengths within inside that piano. If you're playing a guitar, the way you play different notes is by moving your fingers up and down and effectively changing the length of the string. A trombone's a great example. Moving it in or out changes the length of the pipe itself, and that changes the note. So the length of the string or the pipe is a really big factor in which note you actually play. And when we're talking about full musical instruments, that's the thing that allows us to play all the different notes. All right, so we've already talked about how both the ends of the string or pipe along with the length are what ultimately dictates what standing waves are created and what resonant frequencies we hear. So we're going to start talking about the math part of this, and what we're going to be able to do is we're going to be able to calculate which wavelengths will create standing waves, and from the wavelengths we can figure out which frequencies we'll hear when we play a note on a string or a pipe. So the first example we're going to talk about is a situation where both ends are fixed or both ends are free to move, either open open or closed closed, or with like a string instrument, both ends are fixed. And in that case, the wavelengths that will create standing waves are given by this equation right here. L equals m lambda over 2. So L is the length of the string or the pipe itself. Lambda is the wavelengths that will be created, and m is what's known as the harmonic number. And so what that really tells us is whenever we have a given length, okay? There are multiple different wavelengths that can ultimately create standing waves within that length. And those different wavelengths are called the different harmonics, okay? And those of you that are familiar with music probably know a little bit about this, probably more than me, to be honest with you. We see here, like for this given length, we have 1, 2, 3 different wavelengths shown that are creating standing waves within that length, and that corresponds to the first, the second, and the third harmonic here. Same thing for the open-open situation. Once again, we have the first. These ones actually shown, they skip some. This is the third and the fifth harmonic, and the reason I know that is we go right from just both ends fixed to a situation where we have 1, 2 nodes in the middle. So we actually skipped one that would look like this. And same thing going to the last one. But this would be how we ultimately are able to calculate which wavelengths create resonance. And we're going to do a few examples of this, so you'll see a little bit better how this equation works. One thing that is important to keep in mind is that first harmonic is often called the fundamental frequency. This occurs when m equals 1. Okay, so a lot of times you'll hear that term, fundamental frequency, referred to, and what that really tells you is you want to use an m equals 1 in that case. So our second equation is for situations where the ends are different, where one end is open, the other end is closed. The previous one was when either both were open or both were closed. And in that case, the equation looks like this, L equals m lambda over 4. It's a similar setup where L is the length, lambda is the wavelength, and m is the harmonic number. But what's important to note is when both ends are closed or both ends are open, you can have harmonics of 1, 2, 3, 4, 5, etc. However, we see here that these harmonics are only the odd numbers, okay? 1, 3, and 5. And so a lot of times within music, you'll hear the term playing like the octave or the fifth. What that is referring to is the fifth harmonic. And so that's where that term comes from within the world of music. But the basic setup of this equation is the same. We still talk about this idea of the fundamental frequency, which occurs when m is 1. All right. A few examples of this. We've talked about some of these before. An organ would act like this, as would a clarinet, a trumpet, as opposed to the both ends fixed, which would be something like a flute or a guitar. Just want to reiterate this idea again that for any length we have different resonant frequencies which are known as harmonics, and we see them laid out here. Same length of string, okay, but we have a few different modes of standing waves being created. So we see the first, the second, the third, the fourth harmonic, and each time we kind of add one more of these little humps, for lack of a better word, but you're adding an additional node to the standing waves. And as I said before, you do want to keep in mind, and it's on your equation sheet because it tells you what allowed m values there are, but keep in mind that the open-closed pipes only have odd harmonics. All right, so for this first practice problem here, I think it's going to help exemplify a lot of things we've been talking about. We have a scenario where there's waves on a guitar string which is fixed at both ends, so that's going to be the open-open or closed-closed scenario. Either way, it's divided by 2, and they're going to travel at a speed of 409.6 meters per second, and the string is 0.8 meters long. And what we want to do is find the frequencies of the first 3 harmonics. So where I'm going to start is I'm going to start with our equation that allows us to find the wavelength that will create standing waves on this string. And that equation is L equals m lambda over 2. So we're going to use that to start for each of these scenarios, the first, the second, and the third harmonic. And what's going to change each time is that m value, because that m value is the harmonic number. So we know that our initial length is 0.8 meters, and that's going to be equal to m, which is in this case 1, because it's the first harmonic, times lambda divided by 2. So for this first one, we find that our wavelength lambda would be 1.6 meters. For the second one, we're going to say 0.8 is equal to 2 lambda over 2, and the 2's there would divide out. And so what we're left with is lambda in this case will be 0.8 meters. And then for our third situation, we're going to have 0.8 is equal to 3 lambda over 2. And so we have 1.6 equals 3 lambda, so our wavelength here is 0.533 meters. So from there we can go ahead and we can solve for the frequency, and we can do that using the fact that velocity is wavelength times the frequency. So for this first one we have 409.6 is equal to 1.6 f. And so for our first frequency, we get 256 hertz. Moving on to our second situation, velocity is wavelength times frequency once again. So 409.6 is going to be equal to our wavelength 0.8 times frequency. And so we find that frequency here is 512 hertz. And then for our last one, velocity is wavelength times frequency. So we have 409.6 is going to be equal to 0.533 f. So we find that our frequency here for this last one is 768 hertz. And so there you have the first three frequencies, the first three harmonics for waves on this particular guitar string. And I believe the music terminology, this is your fundamental. That is definitely the fundamental. This is the one octave up from that fundamental. This should be a C note. And I believe this would be referred to as the fifth. It's not another full octave up. Another full octave would be 1024 hertz. All right, let's move on to this next one. We have an organ here that acts as an open-closed tube, which means it's going to be the over 4 equation. We want to know what is the length of an organ pipe designed to play a C note with a frequency of 128 hertz. So there's two really important things that we need to keep in mind here. The first is this note that we hear is going to be the fundamental frequency. Okay, the note we hear is always the fundamental frequency. We do hear the other harmonics, but that bass note, what we would say the pitches, is always based upon the fundamental frequency. And the second is the speed of sound in air is going to be 343 meters per second. So that velocity we were using before is going to apply to any instrument where it's a column of air as opposed to a string. So let's start with that speed of sound in air. V equals our wavelength times our frequency. So we can go ahead and say that 343 is going to be equal to our wavelength, which we are trying to find, multiplied by our frequency of 128 hertz. And so when we go ahead and solve for that frequency, or that wavelength, we find that the wavelength here is going to be 2.68 meters. And so from there, we can go ahead and use that to determine what the length of this organ pipe is going to be. And for that, we're going to use our L is equal to m lambda over 4 in this case. And we're going to say that m is equal to 1. As we said before, this is the fundamental frequency. So L is equal to 1 times our wavelength, which is 2.68 divided by 4. And so we find that the length of this organ pipe is going to be 0.67 meters. So I want to just talk conceptually about this idea of harmonics a little bit and how it ultimately comes together to create a nice sounding wave. So what we have here is 3 different harmonics for some instrument. We have our fundamental harmonic here, the second harmonic, and the third harmonic. And so let's just imagine, for the sake of simplicity, this is a guitar. So when you pluck that guitar string, the notes that you hear, the sounds that are produced, are the fundamental, but on top of that, you also produce the second harmonic, third harmonic, and probably to some extent the fourth, fifth, and so on. And so what ultimately ends up happening is these harmonics all come together. They superimpose, they all combine to create this composite wave down here. And what we see about this wave that's important is, number one, it's not a nice simple form. These are all simple waves, okay? They're simple sine waves if we want to get mathematically technical. This one's not. It has little hitches. It's not nice and smooth and consistent, but it does very clearly repeat itself. So it does still have a constant frequency, and we see that it repeats itself every point that I just marked there. So that's the first thing, is it does produce a non simple wave. It produces a more complex wave. And that's really what gives the sound its richness, right? It's very different to hear a C note played on a guitar or some other musical instrument versus just a basic tone that's played at the same frequency. And the reason why is on the instrument you get a much richer sound because of these additional harmonics to create a more complex waveform. The second thing that's important to note, and we can see this here, is that the points where the composite wave, that combination of all these different harmonics repeat, match up perfectly with the points at which the fundamental frequency repeats. So each of these we can trace directly down. And so what that means is the frequency of the fundamental is the same as the frequency of the composite wave. And that's why whatever the fundamental frequency is, that's the note we actually hear. And then these additional harmonics simply add richness and complexity to the sound. So as I was saying before, any musical note is a complex waveform because it's really the superposition of multiple different harmonics. So they all combine. In this case, it's not constructive interference or destructive. It simply combines to create a more complex wave. All right, and that's what gives music and notes and instruments some of their richness in the sound that they produce. The pitch you hear, as I said before, is the fundamental frequency, and then those additional higher harmonics, they go ahead and add complexity. Sometimes they are referred to as overtones. That's another word for them. So you have your fundamental, and then you have the various overtones, additional tones on top of that. But harmonics works perfectly well too. And so the last thing I want to talk about just briefly, and this is only going to be on a conceptual level, is how we're able to actually produce the same note on different instruments, yet they sound different, okay? And so this, and I don't know how accurate this is to the actual waveforms, but it illustrates the idea pretty well. This is showing the same note, a C, on a clarinet, and also on a piano. And what you end up seeing is that these notes, they do repeat themselves at the same intervals, and that means that they're notes with the same frequency here. However, you can clearly see that the two different waveforms look very different. The piano one's a little bit smoother, the clarinet's a little bit more jagged here, and so that's why both of these instruments can produce a C note, and people that know music would be able to identify that note as a C note, but they also would be able to say that even though they're playing at the same frequency, the sound is very much different. And the differences result from the harmonics and how they superimpose and this complex waveform that you get. So this is, I think, a nice visualization of how two instruments can play the exact same note, yet they clearly sound very, very different.